All right, we're going to get started because Gerald was wondering whether we've started. Yeah, Gerald, we've started. We were just waiting for you to come. And now that you're here, we'll get started. Um, I have a couple of announcements. First of all, where are you? You're at the EAS September General Meeting. And I'm here with Brother Guy, and I'm here with Dave Rodriguez. And we decided to all just uh, put ourselves up on the screen and start together to avoid any technical difficulties. I have a couple of announcements. The main announcement is that, as you are most certainly aware, the Chabot Space and Science Center is still closed, but we are still moving ahead to reopen in November. We're starting to, more than starting, we've been doing a lot of work to clean out a lot of stuff that is accumulated. We're doing a cleanup of the telescope makers workshop next week. The EAS has gotten rid of a lot of stuff that has just been sitting around. Ray Wong has been organizing the loaner scope inventory, and we're trying to do everything we can to make the reopening of Chabot coexistent with the reopening of EAS to the public. So stay tuned. We'll probably have some formal announcements of EAS events and Chabot events coming up. And appreciate everyone's patience and assistance if you've been involved in this process. I'd like to give the screen to Dave now, who can introduce tonight's speaker. And as usual, we will wait till the end of the talk to field questions. And you're welcome to ask questions in the chat or Q&A window as you see fit, and we'll curate them and present them towards the end of this evening's presentation. Thanks.
Thank you very much, Rich. It is tonight my very great honor to introduce Brother Guy Consolmagno. He's, of course, director of the Vatican Observatory, which right there says a lot. Of course, he did his undergraduate work and got his master's at MIT and his PhD in planetary science at the University of Arizona. He also, very interestingly, served in the Peace Corps, which just shows how multidimensional he is. And he's currently working on, doing asteroid research, as basically an easy way to say it. Although I know he's also visited Antarctica and looked for meteorites there, which sounds like a tremendous amount of fun. He served as chair of the DPS, the Division for Planetary Science in the International Astronomical Union, and has received the Carl Sagan Medal from the DPS for excellence in public communication and planetary sciences. One other thing I'd like to say also is he's the co-author, I would guess, or author of Turn Left at Orion, which is one of the best astronomy books ever written. And I'm honored just to have you just because of that. My wife loves your book, Doctor. So anyway, without any further ado, Guy Consolmagno, director of the Vatican Observatory.
Great, it's a delight to be here, and let's hope that I can share the appropriate screen. So the title is Astronomical Ideas That Were Almost Correct, and at the bottom here, I'm giving a shout out to a fellow named Chris Graney. Now, as you heard, I had won this Sagan Medal in 2014. That's, so you can see I actually do own a black shirt, which I wear on occasion, though it was kind of a dull gray shirt in that case. The Sagan Medal was so prestigious, and I brag about it so much, but along with the fact that you get the medal, you also are supposed to give a public talk. And so this started as the public Sagan talk that I gave at the World Science Fiction Convention in 2014. It is such an honor because every person who gets a medal gets their own medal with their name inscribed on the back. In my case, it's my name not spelled correctly. That's okay. The other thing, though, that came from this was I started collecting more stories of astronomical ideas that were almost correct, and wound up collaborating with a fellow named Chris Graney. Now, this is Chris and Christina, or Chris and Tina, working in Italy. And it's through him that I've added a bunch of new stories. So if you happen to have heard this talk in the past, this will have new jokes and new stories. It also means I had to, shove off some of the ones because I don't have time for all the stories we've got. Chris and I are working on a series of articles to be published in Sky and Telescope, incorporating a number of these stories. So keep your eye out in future issues of Sky and Tel. The first story I'm going to start with, an idea that was almost correct, was the Aristotelian view of the universe. According to Aristotle, you have not only each of the planets moving in their own transparent sphere between the Earth there at the center and the stars at the farthest edge, all of these spheres rotating at a different rate, including the sphere of the stars, but there is a special physics that goes with it. There are 4 elements, what we would call phases now, solid, liquid, gas, plasma. They identified as 4 elements of earth, water, air, and fire. And each element had its own natural resting place. So the natural resting place of Earth is at the bottom of the universe. If you had water, the Earth would fall through the water. If you have water inside the Earth, it bubbles to the top. If you've got air inside the water, it bubbles to the top. If you've got a flame in the air, it is going upwards. It was all very logical. It was based on what you could observe. One of the things I want to remind you is that the Earth is not the center because it's a special and wonderful place. It's the bottom of the universe. And in fact, the inferno, the place of fire and brimstone where the devil lives, is even further closer to the center. The center is the worst possible place. And these crystalline spheres with each of the planets represent, in later cosmology, the ranks of angels. So the best place is not at the center is the worst place. There were, however, other ideas possible in the Middle Ages. And among the other ideas that came up in the Middle Ages was one by John Buridan, who describes something that we now recognize as momentum. Nicholas of Cusa, who says that, possibly every star is its own world. The point is that the Earth itself that we're on, this round Earth, they knew the world was round, is a part of a universe. And if there's more than one planet, it would really mean parallel universes. In particular, I want to point out something that Nicholas of Oresme wrote in 1377 in a book on the Book of the Earth and the Moon. All motions are relative. If you fire a cannon eastward or westward, and if the Earth were spinning, then the natural circular motion of the Earth would carry the cannonballs in the same distance either way, and you wouldn't notice a difference. So the fact that a cannonball fired to the east goes just as far as a cannonball fired to the west doesn't prove that the Earth is not spinning. Reason alone cannot rule out the possibility that the Earth is spinning and the stars are standing still. That's brilliant. We're talking 200 years before Copernicus. The problem is that he then writes, of course, everybody knows that the heavens are moving and the Earth is standing still. His point is not to argue that the Earth is spinning, but rather that reason alone can't tell you everything that's going on, because reason alone can't prove something as obvious as the fact that the Earth is standing still. So close, not quite. But there is something else that came out of this cosmology. This cosmology is very different from the cosmology of Genesis. It had a flat Earth with a dome. But people were able to sort of transmogrify the Genesis picture into one that fit this cosmology until you get to verse 9 and 10 of Genesis. Let the waters that are under the heavens be gathered together in one place, and let dry land appear, which makes the people in the Aristotelian universe wonder, why do we have dry land? I mean, all rock is going to be at the center, and then water is going to be above the rock. Is it that we don't have enough water to cover all of the Earth? Even if you only had a little bit of water, it should completely cover the Earth, and yet there are parts of the Earth that are sticking up above the oceans. How is this possible? they had a wonderfully clever solution. The sphere of water was pushed to the side of the center of the universe, or the bottom of the universe, so that there was this little dome of dirt sticking above the sphere of the water. And I got these pictures from Chris Graney. Turn it sideways, and you have the Earth, the sphere spinning around the center of the Earth, and this big bulb of water spinning around off to one side with dry land on the other side. And what's going to be at the center of that dry land? Well, obviously Jerusalem, because it's the center of the Earth. Marvelous. That means that when you go sailing on the oceans, you're actually going uphill. That's why they call them the high seas. More than that, when you look at globes that were made before Columbus, and at the top, I've got a lunar eclipse to show that why they knew the world was round. You could see the shadow of the Earth. This globe dates from about a few decades. It's in Germany. All of the Earth is on one side, and the far side of the Earth is all ocean. That's also why Columbus was convinced that he could get to the Indies. Two things. First of all, he knew there couldn't be any land beyond where Spain was, because that was the high seas. He also miscalculated the size of the Earth. Long story of how he did that. And he thought the Earth was a whole lot smaller than anyone else had calculated. Certainly a lot smaller than the Greeks thought. Well, the Greeks were right and Columbus was wrong. But this also explained why you would have fountains of water, because the water would go through the cracks of the Earth and then spew up on the far side. This is from as late as 1663. We're talking more than 100 years after Copernicus. People are still assuming that the sphere of the Earth is offset from the sphere of the water. Even into the 1700s, in a sermon against atheism, we hear that the fact that the water is still pulled to one side is only possible if God is doing it. And therefore, this is a proof of the existence of God. That the sea is higher than the Earth is what men of sound reason have said for centuries. And so there must be an almighty hand holding it back. As late as 1777, so we're now talking more than 200 years after Copernicus, more than 200 years after Newton, for that matter, and 100 years more after Newton, we're looking at people still arguing that this vast sea, of which there's such an abundance of waters that some think higher than the Earth, and yet they are stopped from overflowing and drowning the land. This was how people understood the shape of the Earth. Well, after we're finished laughing at them for their foolishness, go online and you can find images where you are centered on the landmass. And if you include the Americas on the horizon, the point on the Earth that is at the center of where all the land is, including the Americas with the Pacific on the far side, actually isn't all that far from Jerusalem. Maybe they knew something. I don't think so, but maybe they knew something. Another marvelous idea from the 1770s is what we call Bode's Law. Now, like most laws that have a name of somebody, the guy Bode who came up, who's credited with the law, is actually quoting without citing him, a fellow named Titius. And this law appears in the footnote on page 300 and something another of his book on the heavens. This is a copy of the book that we've got at the Vatican Observatory. And you can see in the footnote that the distances of the planets is spaced out according to this law. You start with 4, and then you add 3, and that's 7, divide by 10, that's 0.3 is what Mercury is. Another 0.4 is what Mercury is. Add 3, and then you get to 0.7, which is where Venus is. add 6, which is double 3, and you get to 1, which is where the Earth is, add double 6, which is 12, and you get to where Mars is, add double 12, which is 24 to the 4, and you get 28, which is where the asteroid belt is. Double that, and you get 52, 5.2 is the astronomical units of Jupiter. Double that to 96, and you get to the number of astronomical units where Saturn was. That's what they knew at the time. It was a pretty remarkable collection of a way to estimate where you might expect to see planets. It predicted where the first asteroid, the largest asteroid, was going to be. And then when the Uranus was discovered, it also fit the law. Then they found Neptune, and Neptune doesn't work. I'm reminded of the old statement, proof that all odd numbers are prime. 3 is prime, 5 is prime, 7 is prime, 9 must be an experimental error, 11 is prime, 13 is prime. Neptune, on the other hand, Pluto does work. Mere coincidence? Turns out, yeah, it is mere coincidence. The numbers only work if you kind of half close your eyes and allow yourself a lot of leeway, because Saturn really doesn't work all that well. Neptune doesn't work at all. Venus and Mercury are significantly far from where this is supposed to be. It's one of those patterns that if you really want to believe in it, you'll ignore the fact that it actually doesn't work. But the world is even more complicated than that. About 15 years ago, it was worked out when people were trying to figure out why is there this collection, why are the planets where they are, and did they interact with each other? A large theoretical model for the outer solar system had all of these green dots out beyond Neptune and Uranus. And then going inwards, we've got planet Uranus, the purple one, Neptune, the blue one, Saturn, the yellow one, Jupiter, the red one. As Jupiter is throwing material that we now have in the asteroid belt outwards, it gets into a resonance with Saturn, which then flips the position of Uranus and Neptune. We really think something like this happened in our solar system because we find this in other solar systems. We find that planets have migrated tremendously. So not only does Bode's law not work, it really shouldn't work, because the planets where they are today is not the planets where they were formed. Now, you notice I've got a great gray beard here. This is what happens when you get gray hair when you're an astronomer. You get more and more into the history of astronomy. And most of what I learned is historical. One of the things I learned 50 years ago at MIT, it must be true, it was at MIT, was that there are two kinds of planets. You got the small rocky planets close to the sun, and the big gas-rich planets far away from the sun. And all the planets are in the same plane. And any theory to explain the origin of the solar system has to be able to account for this pattern. Well, if all the planets were formed out of a large cloud of gas and dust, and the gas and dust is spinning, in the spinning, you will have centrifugal force essentially holding up the gas and stopping it from falling in the plane, but above and below the disk, it's going to collapse down to the surface. So you will wind up with a disk full of material. The disk that is closest to the sun is going to be the warmest. So any of the hydrogen and the gaseous compounds, including water, will be a gas. You'll only get planets made out of rock in the inner solar system. There is this magic line between the asteroids and Jupiter where suddenly water is cold enough to condense, and you've got twice as much water as rock. So suddenly you've got big snowballs that can grow so fast that they can trap the nebula gas, and that's where you get gas giants out beyond the frost line. This explains everything we see. It explains why the planets are in a disk. It explains why the rocky planets are close to the star and the gas giant planets are farther away. It also explains why in our solar system, there's this huge gap. This is on the left, that's a logarithmic, scale. There are no planets in the size range between Earth and Neptune, because as soon as a planet is big, has enough water ice that it can accumulate something bigger than Earth, it will be big enough to trap the gases of the nebula, and it will immediately jump up to become a gas giant planet. This was the beautiful theory that I was taught 50 years ago, which explained all of these patterns in the solar system. And then we discovered other solar systems. The first thing we discovered were gas giant planets orbiting, essentially inside where Mercury is in our solar system. They were obviously migrating by this pattern that we saw in the NICE model, the NICE model as it is. The other problem is, after we've discovered a few thousand planetary systems, the size ranges of the planets that we discover are primarily in the gap region that our theory explained why you would never find a planet there. Great. We had an explanation for something we didn't see until we saw it, at which point you go, maybe there's something wrong with the explanation. It was a great idea. It was almost correct. One of my great heroes of astronomy is Giovanni Scaparelli. Schiaparelli, and some people want to mispronounce it Schiaparelli. His name is Italian, so the SCH is a hard ska. He was possibly the greatest astronomer of the second half of the 19th century. And I want to concentrate on three remarkable things that he was able to do. The first was he was able to observe Mars with a big telescope really carefully, seeing the patterns of the light and dark, which are actually there, which you can see in photographs today. Unfortunately, he was also fooled by optical illusions, which cause you to think when there's a bright region and a dark region, your eye can be tricked into thinking that there are thin lines that are connecting them. It's like turning on unsharp masking and overemphasizing the difference. He decided that not only were these big channels there, the way that other people had suspected, even using the word canali, but he thought that there were thin lines. The crazy thing is, the dark regions that he saw were real. The maps that he made of Mars are still, the terminology on those maps are still what determines the terminologies we use to this day to describe the different regions of Mars, like Syrtis Major here. You may recognize this globe and this image both have south at the top, because that's what it looks like in a telescope. There was something else beyond being a really close observer of Mars that he's famous for. He was able to observe Mercury and find markings on the surface of Mercury, and to watch these markings and calculate how much Mercury was spinning. And when he saw Mercury so close to the sun, spinning so carefully, he writes, and this I'll translate the Italian, immediately and without any further calculation, the duration of the rotation is equal to that of its sidereal revolution, which is to say 88 days. Schiaparelli's careful observations of the spin of Mercury showed him that Mercury always keeps the same face to the sun. Except when we started shooting radar off the surface, we discovered that Mercury doesn't spin with an 88-day period, but with a 59-day period. Was he just making this up? No, he was actually seeing real things. The trouble was this. As you know, Mercury is really only easy to see when it's far from the sun, and that has, comes about 3 times a year, the same times of year over and over and over again. And some of those are easier to see than others. Even when Mercury is farther from the sun, if the ecliptic is closer to the horizon, it's still harder to see Mercury because it's also closer to the horizon. So there's a real limit to when you can see Mercury and observe it carefully. Schiaparelli tells us the days when he observed Mercury, and these are the days in question. And the period of days between each observation is roughly 120 or 240 days, which is 2 spin periods of Mercury. Because of the nature of not just Mercury's spin period resonance, because 59 days is exactly 2/3 of its rotation period, but it also has this odd resonance with the period due to the position of the Earth compared to Mercury, when you can actually see Mercury. It was like, the wagon wheel in Western movies where you can see the spokes and sometimes they even, seem to drift backwards. It was a stroboscopic effect. He only observed Mercury when it was in the same orientation. And the dark spot that he was seeing on Mercury was in the same orientation. In other words, he was a great observer. He could see things better than anyone else, and he saw them. And he went immediately to a conclusion that was completely reasonable, but wrong. So he saw the canals that weren't actually there. He saw the spin of Mercury, which he got wrong. The most frustrating to me, though, was what he did with shooting stars. As you know, there are days when there are going to be meteor showers, but when you follow these showers, which occur roughly the same day every year on Earth, there are some years that have much stronger periods. Schiaparelli noticed that there was a particular periodicity to meteors. You see, this is the HA ray diagram of the constellations. Over to the left there is Leo the Lion. When you put the Leonids, you can see why they're called the Leonids, because all these shooting stars seem to be originating out of a point where Leo the Lion is. And Schiaparelli was able to explain why the Leonids came through there. He said, basically, the Earth is going into a stream of meteors every time, and that particular day when it's in that position of its orbit around the sun, when Leo happens to be on the far side. That's why suddenly there's a burst of meteors only visible really well in the nighttime side. He was the one who recognized that the dust that gives us meteor showers were in a ring like that. And not only that, he knew that the Leonids had this especially strong burst every 33 years, which he then said, okay, that's the period of the orbit. From the direction of where the rocks were coming from, the position in the sky, he could even work out the semi-major axis. Well, of course, you get the semi-major axis in the period, Kepler's law, but the perihelion distance, eccentricity, inclination, he was able to work out the orbits, the shape of the orbit of the dust that made the Leonids. And then he recognized that that was exactly the same as the period of comet Tempel-Tuttle. That was brilliant. Even knowing that that's the answer, I don't think I've got the math to be able to figure that one out. That's brilliant. We now know that meteor showers are affiliated in every case with some well-known comet, or in some cases, a very dusty asteroid. So what's wrong with that? It's a brilliant piece of science. Except that he then argues that we know stuff falls together because gravity attracts things. So it must be the case that comets are formed by the infall of dust. And what we're looking at here is the growth of comet Tempel-Tuttle. Rather than, as we know now, it's the comets are falling apart and the dust is being shed as the ices turn into gas and blow the dust off. So close, so brilliant, and so wrong. Well, There's one last story I want to tell on this almost correct, and it's a story on myself. It started, about 20 years ago when I'm reading the Harry Potter books, and I think it was, Goblet of Fire or one of them. Hermione is looking over Harry Potter's homework, and she says, Harry, you've got this wrong. The moons of Jupiter are not covered in mice, but ice. She's talking about the moons of Jupiter being covered in ice. That was my thesis at MIT. There it is, thermal history models of icy satellites. And yeah, that's what I looked like in 1975. Never mind, it was the 70s. The first draft, I'd given them a title, and then when I typed it up, I typed it wrong, so I had to go and correct the first page. I did go back and reprint that out. But the point is, in 1975, working on a brilliant idea that my advisor had, it wasn't my brilliant idea, that the moons of Jupiter were a mixture of ice and rock. If the rock gives off a small amount of heat because of the small amount of radioactive materials in the rock, then the rock should cause the ice to melt. And you'll wind up with a rocky, maybe even a metallic core, and then a liquid ocean with a thin covering of ice at the top. That was the idea. My thesis was to actually write a big old Fortran problem, a deck of cards, to calculate, would this really occur? Is there enough heat generated in the rocks? Will the water actually, move away from the rocks? Is the force of gravity strong enough to move things? And basically, that's what I did. So mine was the first published calculation over time of how the moons of Jupiter and Saturn, the other icy moons, would evolve with time, 1975. 20 years later, in the 90s, the Arizona Press had come up with the idea of a big book about Europa. And they said I was invited to be one of the authors on the first chapter. Hey, this is great. My work is finally getting recognized, because these drawings are not my drawings. These drawings were by a bunch of guys at JPL who had the same idea, but didn't do the work as much as I did, but they had much better artists than me. So they got the credit for the idea. Those guys, finally, I'm getting my name in the book. I'm going to be, in the chapter. I'm going to write up. Well, the chapter that I was writing this all up was actually not our current understanding of Europa, because my models were fundamentally wrong in a couple of ways, and we won't go there. What my chapter was the history chapter, the history of what we used to think we knew about Europa. Okay, yeah, by 1995, my ideas of 1975 were 20 years out of date. Maybe they're right. So I write up my, history of how we had come up with that idea. And then I noticed the rest of the chapter leaps immediately from Galileo discovering the moons of Jupiter to me making, thermal models with Fortran cards. Surely something else must have happened in our study of Europa before then. In particular, how did we know that Europa was a mixture of ice and rock? I started my work in 1972. That was before any spacecraft had been to Europa. That was before we even had spectra in the infrared showing lines of water. But we knew that Europa was a mixture of water and rock. We already knew that. How did we know that? Well, there were two things that I had been taught, which are still true. One was that the albedo of Europa reflects 64% of the light that hits it, which compared to 12% of the light that hits the moon. Europa is a much, much brighter place. There's not that much stuff in nature that will reflect 60% of the light that hits it. Ice, somewhat dirty ice, will do that. And the list of other things that will do that you would expect to actually occur in bulk in the universe starts at ice and it kind of ends with ice. Maybe other ices. The other thing that we knew, though, was the density of these moons. Because if you saw that the surface was ice, how did you even know there was any rock in them? And you knew that from the density. Density is mass divided by volume. All right. When did we first know the albedo of the moons of Jupiter? And when did we first know the density? When did we first know the mass of the moons of Jupiter? When did we first know the volume? How did people figure that out? And who was the first person to put all of this together to say that Europa is a mixture of ice and rock? And in fact, from its density, it is really mostly rock, which meant that it melted really completely, which meant that there's this thin but pretty clean surface. Who knew that? Oddly enough, the first number to come up was the mass of these moons, because Laplace had worked this out in his theories of 1803. Finding the mass of a moon is really hard because, well, remember what Galileo said, you drop two things, the smaller thing and the heavier thing are going to fall at the same rate. So they're going to orbit around their planet at the same rate, because what's an orbit? Just a fancy fall. But Laplace was looking at how one moon perturbed the other moons. And with 4 moons, he could work out the mutual masses. Now, mind you, he could only work them out relative to the mass of Jupiter, but he knew the mass of Jupiter because he knew how quickly the moons were orbiting around Jupiter. So that tells you the mass of Jupiter. Of course, you also need the value of big G, because the acceleration is big G times the mass divided by the distance between them squared. Big G was measured by Cavendish in 1795. So they had all the figures they needed by the early 19th century, in the 1800s, to measure and indicate. And you look up the masses that Laplace calculated compared to the masses we believe today with a lot better observations. He was really good. The 3 inner moons, he got to within 10% of their actual mass. Callisto, 25%. But for those days, that was phenomenally good. What was much harder was to get the volumes, because these things are dots of light in your telescope. You have a hard time actually measuring, except in a really good telescope, the size of these things. What you can measure, though, is how long it takes for them to pass in and out of the shadow of Jupiter. And you know how far away they are, thanks to knowing the number of AU. You know how fast they're moving, because you can measure that. And so you can see by how fast they go into or out of a shadow, you can work out the sizes of the moons. And that gave you reliable volumes. It also gave you reliable albedos, because the albedo is how intrinsically bright is the surface. Well, if you have a really big moon that's dark, it's going to reflect as much light back to you as if you had a really small moon that's bright. By knowing how big the moon is, then you can work out from the amount of light you actually get through your telescope, whether it's small and bright or big and dark. This was worked out by the middle of the 19th century. So I went to our library at the Vatican Observatory, where we've got a collection of wonderful books from the 19th century, textbooks, popular books, and they all talk about the moons of Jupiter. And they all list them, usually as moon 1, 2, 3, 4. It's rare that they use the names that we use now, even the names Io Europa, et cetera, where had been around since Simon Marius. But they'll list the 4 moons, and they will list, where they're orbiting, and they will list how big they are, and they will list how massive they are, but they never divide the mass by the volume. They never ask, what is the density of the moon? Because astronomy in those days was a field of mathematics that was designed only to calculate orbits. They didn't think of the moons as places that you could walk around on. They never bothered to ask themselves, what were the moons? Merely, where were the moons? Now, in particular, I have two books here among our collection that I want to look at a little more carefully. The one on the left, Popular Astronomy by Simon Newcomb. Newcomb was the Carl Sagan, the Neil deGrasse Tyson of his day. Brilliant astronomer and a great popularizer, so he was quite famous. In fact, Moriarty in the Sherlock Holmes stories is probably based on him. And in his book, I read, here's the size of it according to the best determinations. He's got that right. The light of the satellites varies to a degree that it's difficult to account for except by supposing changes going on their surfaces. But wait a minute, what? Nobody ever told me that the brightness of the moons of Jupiter changed radically. But here he's got all the careful measurements made by these eminent astronomers, Germans, so they must be right. And you can't, of course, see their surfaces because they're so far away. What's going on? Why is it, and I found this in many books, everybody agrees that the moons of Jupiter change their brightness. The best they can come up with is either, there's a bright side and a dark side, but it's random. It's not according to where they are in the orbit. The most common explanation is that these moons must be spinning so fast that they have compressed themselves into a disk, and the disk is tumbling. So sometimes you see them edge on, sometimes you see them face on, and that's why sometimes they're bright and sometimes they're dark. And I'm thinking, nobody ever, I've looked at the moons of Jupiter a zillion times through my little telescope. I've never noticed their brightnesses varying to a wild extent like that. But everybody in the 19th century seemed to have seen that. That's weird. Then I came across this other popular book by a fellow who is just a school teacher. He is not an astronomer, published in London in 1861. And he's got the tables of the satellites of Jupiter with the names, and he includes their densities, because he's got the masses, which are pretty correct, and the diameters, which are pretty correct, and the densities. But when you look at the densities, there's something odd. The density of Io is 0.1 times the density of water. Water is 1 gram per cc, so 0.1 grams per cc. 0.17 grams per cc, 0.3. I got a question for you. Can you think of anything in nature that has a density of 1/10 the density of water? Balsa wood is the only thing I can come up with. And nobody's suggesting these guys are made out of balsa wood. These numbers are goofy. They can't be right. So where did he go wrong? I actually measured his mass divided by his volume, and I come up with numbers that are much more reasonable, off by a factor or two, but still possible. Where did he go wrong? The more I've puzzled over this, I have no idea what mistake he made, because the mistake isn't even uniform. It's not like he was doing the same thing wrong over and over again. The first number is nearly 10 times what it should have been given his mass and his volume. But the second number is 11 times. The third number is only 4 times. I have no idea where he went wrong. But he went massively wrong and didn't even ask himself, did these numbers make sense? Could these numbers be real? He never even asked the question, because he's still in a world where nobody asks, what are they made out of? Just where are they? Finally, at the end of the 19th century, Pickering revisits this question. And Pickering was a director of the Harvard College Observatory. And this is where my office was when I was a postdoc at the Harvard College Observatory, so far ago that I'm a third of the number of years back to when Pickering was running the place, in the 1970s instead of the 1900s. He's got a table. He's got 2 different possible diameters and densities, and he's got albedos. The first thing he has done is he's worked out a new way of measuring the albedo. How did they measure the brightness of the thing in a telescope? Well, anybody who's done double stars or variable stars know how to do that. You look at the object, then you look at a standard. He decides to use Jupiter itself as the standard, and he has a thing in his telescope that separates the light from the moon and the light from Jupiter, and he's got crossed polarizers that we can twist so that the light of Jupiter is dimmed down to match the light of the moon. He sees how far he has to twist it, and he comes up with the fact that the moons have the same brightness. During the past 2 or 3 years, I've compared the satellites. In no case have I been able to perceive any marked change in their relative brightness. Beyond that, due to the proximity of Jupiter. Well, yeah, if the detector you're using is the human eye, and you're looking at how bright it looks to the human eye when you're looking at Europa, and Jupiter happens to be in the field of view, your eye is going to be shrinking down to account for the brightness of Jupiter, and Europa is going to look like it's dimmer. And that's why people who were carefully comparing the brightness of Europa at one time when Jupiter was in the field of view and another time when Jupiter was not in the field of view, were getting different brightnesses of Europa. Phew. So one problem, we no longer have these magically brighter and darker objects. He then works out the densities. And he notices that they are extremely small for solid bodies. You know, density of 1 is a whole lot different from the density of the moon, which is around 3, the density of the Earth, which is even greater. That means that these moons are either, covered in thick clouds, which is not likely because they don't have enough gravity to hold the clouds together, absolutely true, or they're made out of something which is bright and low in density, which is absolutely true, to which he concludes they must be made of heaps of loose white sand. Why did he say white sand? He never thought that they could be made of ice, apparently. But more to the point, how else can you have a moon squeezed down to a disk unless it's made out of loose material? Why is it squeezed down to a disk? Because that was how you explained the varying brightness, which several pages earlier he said didn't exist anymore. So brilliant and so wrong. Almost correct. It's not until 1923 when the geophysicist Jeffreys does the same calculation and says they're made out of ice and rock. Why was he making this calculation? Because he was really interested in trying to figure out what Jupiter and Saturn were made out of. And he had concluded that they must be made out of ice too, and because after all, they've got a density of around 1. And even though he's a geophysicist, it didn't occur to him that you could have a giant body made only of gases, or primarily of gases, so compressed that their density would finally mimic the density of ice by a coincidence. Once again, so close, but almost correct. Now, I brought in my own work to this. That's because in my famous thesis of 1975, I ended by writing that the last sentence. You've got mixtures of rock and ice. You've got water percolating through the rock to get to the surface. The rock might have some carbon in it, might even have carbon-bearing ices. There should be organic chemistry happening in that water, but we stop short of postulating life. I love the we, the royal we. We stop short of postulating life forms. We'll leave that to others more experienced than ourselves in such speculations. What a snotty 22-year-old I was back then. Because what I was thinking of course, who was coming up with the idea that there was life everywhere? Carl Sagan, whose face is on the medal that I won. So embarrassing. But what's worse than that was The first time I presented this was at a meeting at the University of Arizona in 1975. And I came up to him and I said, you know, there might be life in these oceans. And Carl actually looked at me and said, in order for there to be life, you've got to have an energy source. And if this ocean is covered by, you know, a 10-kilometer thick crust, no sunlight is going to get there. And if there's no sunlight, there's no possibility of life. And I go, I should have thought of that. So I never in that talk or ever again talked about life. So I'm not the first guy to propose life in the oceans of Europa. I'm the first guy to specifically not predict life in the oceans of Europa. Within 5 years, in the darkest parts of our own ocean, we see thermal vents and life that lives from the energy generated inside the Earth by radioactive materials, just as I had thought was going on in the moons of Jupiter. And that is the energy that actually could sustain life, maybe even in the oceans. And this was described in a paper by 1983, you know, 8 years after my idea, except they wrote the real science. I was just dreaming science fiction. Steve Squires, the second author, was a grad student of Carl Sagan's. But he gets the credit. They get the credit because they did the science right. I was close, but I was only almost correct. Well, the moral of the story of all of this is that science is going to make mistakes, but you learn from your mistakes because you learn how to correct the mistakes. We now know something about the formation of planets we didn't know before because we discovered that our old ideas were based on a very naive system of, you know, rocky stuff still is probably made closer to the sun, but there's an extra factor that we didn't understand, which led us to realize this nice model of planets migrating. More often, though, the mistakes aren't in your data. The people in the 19th century had the right data. The mistakes are in your imagination. It could never occur to you to think, oh, there might be ice in that part of the world. It would never occur to you that, oh, maybe there's gas blowing off of a comet causing the dust to go out rather than in. Finally, I want to take one last look at this wonderful JPL image of a planet where you've got different spheres of material, including a transparent sphere of water and then a sphere of crystalline ice. Imagine, if you will, if you were an intelligent tuna living in that ocean, there would be no way that you would know that there was a universe above the ceiling that you encountered or below the bottom of your ocean. You couldn't see the stars unless maybe there was an impact that cracked the surface and you're swept up just for a moment through the surface to see Jupiter and a universe that's full of stars. A sense of imagination of a universe of crystalline spheres that takes us back to the the medieval era. Thank you very much for my talk. And if you want to know more about the Vatican Observatory and what we do, go to our website, vaticanobservatory.org. And at that, I'll be happy to take questions.
Well, thank you so much. That was a wonderful talk. Before we do questions, there's something I want to share. And not all of you know that Brother Guy has an asteroid named after him. And I have this photograph taken from our own 36-inch research reflecting telescope of asteroid 4597 Consolmagno.
I'm so there's something that shows that this is not serious science. I'm sorry. It's the fact that the font you used was Comic Sans.
Yeah, that's right. That's because the person who took the photo is a comedian.
Perfect. No, that's great.
And since he can't speak and defend himself, but is watching right now, I'm sure I'll be hearing about this later.
Oh, that's excellent. That's excellent.
So I wanted everybody to see that because we had fun with your asteroid. So we do have some questions. Let me see if I can find where these ended up. Pardon me for a moment.
Gerald says he's not a comedian, he's a clown.
You know,
I think
I'm
we're
gonna.
all clowns in this world.
Yeah.
We're all bozos on this bus.
Well, the ones that are having fun certainly are.
Yes.
When and how did scientists determine that Jupiter lacks a solid surface? I think that's a great question.
It's a
Based
great
on what you're
question.
talking
And
about.
clearly by the 1920s, they hadn't worked that out. By 1970, everybody knew it. So I haven't done the exact, I don't know the person who actually did that calculation, but my guess is probably it was the early 1950s. It may even have been Jeffreys. He was the greatest geophysicist of his generation. But there was another case that he was looking at the idea of plate tectonics and showed definitively that you could not have plate tectonics the way that it had been described in 1910. That wouldn't work, and therefore he didn't believe in plate tectonics. But I would bet that he was the one who worked out the amount of compression you would get. It's a fairly complicated calculation, especially because the center of Jupiter and Saturn are they're degenerate, and you really have to start doing quantum physics to calculate their density correctly.
But it was such a deviation from the prior belief. You know,
absolutely.
It's dramatically different, and it's very interesting.
I would put it at the 1950s, but I'd have to actually look it up. Go through some old textbooks and see which ones talk about it.
You got a compliment on your Europa and Jupiter moon animation,
which I swiped off the internet. I have no idea.
God,
I put that part of the talk long ago enough that I've lost track of whose it is.
The person who asked that, it was Rich and Sue. They wanted to know if you had any thoughts about Pluto.
That's a whole different talk. I've tried many ways of expressing this, and when I was part of the committee that had to determine it, and we argued endlessly about it. I was one of the people who voted, and I wanted to vote that dwarf planets were real planets. I was wrong. As soon as I started teaching it, I realized how much easier it is to say all the planets have these characteristics rather than all the planets have these characteristics except Pluto, or except Pluto and Makemake, or except Pluto and Makemake and Eris. The other thing, since I study these trans-Neptunian objects, is to recognize that they really are different things. They're made in a different way. They're put together differently. Their history and their science is very different. When I'm trying to classify and find the data on them, I want to find them in the pile of data that includes trans-Neptunian objects, because that's what I'm going to compare them against, not the pile of data on the page that has planetary data. But people have prejudices, and I know that. And I finally realized the only way is to attack the prejudice head on. What makes you think that being a planet is better than being something else, better than being a dwarf planet, better than being a star or an asteroid? You're guilty of planetism.
Planetism. Yeah, I know a couple of planetists who will probably take issue with that. Again, I'll be seeing them later. Marianne, you wanted to know if the talk is recorded. Yes, and I will be sending out an email with a link so you can watch it again and show it to any friends. So we'll take care of that, and I hope to have that done by the end of the weekend. Frank asks, when did somebody point out that your models of thermal evolution of icy moons had rock ice mixtures with higher densities floating on salty water of a lower density?
That actually didn't happen in my models.
Okay.
What happened is you started out with a rock and ice, all of one density. The material inside would start to melt, and the rocks would fall down to make this core, and the water would percolate up. But of course, as we know, ice 1 has a lower density than water. So that's why you would have the ice floating. These objects are big enough that you would actually have an unstable situation for a while where the rock and ice above the layer that's melting is more dense than the water. And that was the first big mistake that I made, because we now know that this density difference would cause an overturn, which carries the molten water up, which means that you're carrying the heat of the molten water up, which means the heat is escaping essentially 10 times faster than my thermal models predicted. The other mistake is radioactive elements is not where the heat's coming from. The heat is coming from the tidal flexing, which is 10 times more than the heat I was calculating. So my models underestimated the heat flow by a factor of 10 and underestimated the heat generation by a factor of 10, which is why they predicted what we saw. They got the right answer for the wrong reasons. And yet, even so, wrong as my models were, they gave people something to look for. And when you didn't see what you expected, you could then say, okay, why is it this way?
What I loved about this talk is it really does show how science works. And I think that that's part of your goal here. I was wondering, and pardon me if it sounds like almost a rhetorical question, but I'm wondering if you have any thoughts about the state of science education in America right now, and where we are going wrong, and what we can be doing about it.
What we can be doing, I have no idea. There are three things I'll say about science education. When you teach somebody Shakespeare, you teach Shakespeare in a social setting. You teach the ideas that Shakespeare is trying to get across. You teach the characters that Shakespeare is showing you. What you're not teaching is how to write an iambic pentameter. You're not training people to write Shakespeare plays, but to understand Shakespeare plays. And yet, when we teach science, too often we're teaching people how to be scientists. And that closes off 90% of science. The second thing is that we're teaching science as if it was a big book of facts. And as you can see, the facts are only where we start in the story of science. The facts are a great way to know that you've worked out the problems right, but science isn't working out problems to get the answer in the back of the book. We have to do that the way that we teach music. You know, if you're going to get somebody to play the music, you have to teach them scales before they can play a song, but scales are not music. If you're going to teach somebody to be a physicist, they have to get the answers in the back of the book before they have to get used to how physics works. And I can understand that. But that's if you're trying to teach them how to be scientists rather than to appreciate what science is. There is a whole generation going back, 50 years of people trying to write physics for poets classes. And they've generally been unsuccessful. The places where I've been most successful, and you notice in this story, is I don't talk about things without talking about people. So I mentioned Schiaparelli and the mistakes he made as a human being. I talk about, Percival Lowell. I talk about Jeffries. People love to hear stories about people. And when they realize that science helps you get the joke, helps you appreciate what the person was doing, and you put it in the context of what people thought was truth at the time, that's in some ways a more successful way of communicating the bigger picture of what science is, maybe. But when you teach it as absolute facts in the back of the book, and then we discover that the fact in the back of the book was wrong, Pluto really didn't belong in that table, it belongs in the other table, people get upset. Or people will say, you see, those scientists don't know anything. And both of those statements are wrong. But science is this human process of getting used to the universe rather than a collection of unshakable data. I run into the same problems, incidentally, in the religious world. People think they know who God is, and they want to, close their mind and not be open to learning anything more about their own religion. The joke is that you stop learning religion when you go to confirmation class or bar mitzvah class.
I have a question tangential to what you just said. Have you ever discussed astronomy with Pope Francis? And what did you talk about? And did he ever look through the telescopes at Castel Gandolfo?
He's been to the lab and we've shown him meteorites. We didn't have a deep conversation about the science itself. He's very aware of the science. He's got a background in chemistry. He worked as an industrial chemist before he became a priest. But what the popes, and I've been around for 3 popes, what they tend to do is they talk about things like that they know are important to know, but outside their comfort zone. Mm-hmm. They talk about it with their friends who can speak the language they grew up with. So John Paul II had a group of Polish scholars who would meet with him every summer to let him know what was going on in the world of scholarship. When Pope Francis wrote Laudato Si, that encyclical about the environment, he relied on Argentinian scientists who could explain these things quite well. Mm-hmm. So that's not the sort of thing. We've had some interactions, which I won't go into. They're all very good, but they tend to be private. He'll be looking for something to say. I can say, go. But when he says it, he's saying it. I'm not saying it. So it's not up to me to say that. The closest I had of a conversation like that was with Pope Benedict, who also visited our lab. And I was showing him one of the Mars meteorites, and he immediately said, why do we know it's from Mars? He was curious about that. He understood the explanation. Benedict was very, very bright, as anyone, no one doubts that he was just a brilliant scholar. He's also got a wickedly good sense of humor. And you'd never know that, because when he was speaking in public, he was always lecturing like a German professor, because he was a German professor. But in small groups, he was just charming and marvelous to be around.
That's wonderful. Thank you.
All right. Well, thank you for joining us tonight, and I really appreciate you taking the time. I know you're 3 hours ahead, and it's been a long day for you. And to everyone, we'll have this up on our YouTube channel.
I see 2 more questions in the chat, which I can answer quickly.
Great. I'm glad you saw them. I missed them.
Okay. Does the model of orbit flipping explain the spin axis of Uranus? Probably not. We still think that was an impact similar to the impact that made the moon out of the Earth. So we know that these big impacts do occur when planets are forming. That's today's favorite theory. And any thoughts on the interpretations of Oumuamua? It's not a spaceship. It's not Rama, It's what's fascinating, the people who do the models, they say that at any given moment, there's probably some interstellar interloper somewhere between Mars and the sun, but most of them are so small and so dark that we've never noticed them.
Yeah, for those who are interested, we had a great talk by Tim Thompson on Oumuamua last year. So I think that's on our YouTube channel. So if you want to know about that in more detail, it's worth checking out. So anyway, thank you again. And Dave, we do have to close the meeting. So
I'll be very quick. I just want to announce that next month's speaker will be Dr. Ekta Patel from UC Berkeley, and should be talking about galaxy dynamics. We have that meeting scheduled for October 23rd, which is the same night as the Chabot Gala, unfortunately. We may try to move that to Saturday, October 16th. Stay tuned.
Yeah, we'll send a message out to everybody if we are going to move the date. It would be nice if it didn't conflict with another major event that many of us are participating in. So, all right. Thank you, Dave. Thank you, Brother Guy. It was great to see you again, and wish you the best.
Okay. And for all of you who I couldn't hear laughing, I hope you got a few chuckles out of the talk.
Oh, definitely. I was laughing throughout.
And we'll have to have you in person.
Yeah, absolutely.
I really got to get out there.
We'll invite you back. That's right. All right. Take care now.
Bye-bye.
Bye-bye.